Welcome to today's webinar in the Knowledge Mile series, part of the Lord Mayor's lectures on behalf of Alderman Professor Michael Mainelli, whose theme for his mayoral year is Connect to Prosper. In this free online lecture series, we address the connections in and around the square mile, which Michael likes to call the world's coffee house, and how these might help us to tackle future global challenges. I'm Professor Tim Connell, Chairman of the Gresham Society and a Fellow of Gresham College here in the City of London. And I'll be convening this session and moderating the questions and answers in the lecture. This is the plan for today. A few minutes for me, then the keynote presentation from Professor Sarah Celebras, and then we'll have 20 minutes or so for questions, which I'll be moderating. Now, let me introduce today's speaker. We're delighted to have with us Sarah Celebras, who is a professor in soil mechanics at City University of London. Sarah, perhaps you could tell us a bit more about yourself.
So thank you, Tim. As Tim has said, I'm a professor of soil mechanics, and this means that my specialism is civil engineering applied to the ground, or ground engineering. My particular focus is on how the soil responds mechanically when we build on it or in it. And I've been undertaking research in this area with my colleagues at City University of London and collaborators from the civil engineering industry for almost 30 years. I'm also very much involved in teaching and supporting students who study here at City. And in my spare time, I'm an active member of the Worshipful Company of Skinners, primarily acting as a school governor.
Oh, very interesting. Now, can you tell us a bit more then about the future of building foundations in the city and where and how the energy generating assets fit in?
Yes, thank you. I'm just going to share my screen. Okay. And so this morning I'm going to talk about a recent collaboration with Keltbury Piling to develop an idea for a novel type of foundation that my colleagues, Professor Neil Taylor, Dr. Andrew McNamara and I originated here at City. In the talk, I hope to explain how research can inform and support innovation from both academia and industry. So the title of my talk is The Future of Building Foundations in the City, Energy Generating Assets. So in the City of London and London in general, we need to provide foundations for high-rise buildings because London is densely populated and has really substantial residential housing needs. And these can only really be met by high-rise buildings. In the City of London, we also have a number of high-rise commercial buildings, as shown in the picture. As those of you familiar with the city will know, there's a constant cycle of redevelopment of these buildings. You just need to wander around to see it. And if we want to achieve net zero by 2040, which I think is the aim of the City of London, we need to reuse as much as possible of the buildings we redevelop, including their foundations. So what are these foundations? So high-rise buildings in London are supported largely on deep pile foundations, which are constructed in the strata underlying London, as shown in this simple geological section of the London Basin. London clay is the major strata beneath London, underlain by a mixture of clay, silt and sand, and then the chalk. The depths of these strata vary quite dramatically across London, so that whilst it would be convenient to just construct foundations in the London clay, many will go down into underlying strata, even as far as the chalk. So what is a traditional pile foundation which we use to support these buildings? Well, these sit in the London clay and are generally cast in situ piles. And for these type of piles, you excavate a bore, a circular hole in the ground, you suspend some steel reinforcement in that bore, and then you fill the bore with concrete. You then have a pile which will take some of the load of the high-rise building that you construct above it. The majority of that load that acts on the pile is taken in shaft friction. And if you want to take more load, you have to either increase the diameter of the pile or make it longer. You can put pipes in these piles before you put the concrete in, sort of around about this stage here. And and then you can circulate water through them, and that will give you a thermal pile for heating and cooling your building. That type of thermal pile is quite common in mainland Europe, not quite so common in the UK. So why is this approach not really sustainable? Well, to start off with, there's a lack of space beneath the buildings because of the foundations from previous buildings. And if we keep putting more and more foundations in, we're just going to fill up the ground with concrete, which is not really what we want. We cannot achieve carbon zero, and that's because we're using carbon in order to create our foundations. And even if we use the piles for heating and cooling, we're not offsetting that carbon that significantly in a conventional pile, because that process isn't very efficient in a conventional pile. And we're not reusing our foundations, and so the new piles that are installed are often not sufficiently efficient in the way they carry the load. So these things mean that whilst we're constructing foundations that hold up the building, they're not a long-term asset for the building. So let's think a little bit about the lack of space. So this is well illustrated when you look at these two buildings here. So this is Bucklersbury House, constructed in 1959, let's say early 1960s. And this is the Bloomberg building, which was constructed in probably the mid-2010s, towards the early, mid to late 2010s. And you can see that they're roughly the same height of building, so one's not a huge amount larger than the other. But the foundation solutions are quite different. In the 1960s, the method of creating pile foundations was something called tripod piling, and that meant that you put in loads of small diameter shallow piles, which you can see on the left-hand side. So this tripod piling going on in the 1960s. In contrast, the Bloomberg building was built on a much smaller number of large diameter piles, which is much more fashionable now. And those large diameter piles clashed with and had to be fitted around this forest of smaller piles. And you can see this forest of smaller piles when you look on the right-hand side of the picture, and you can see archaeologists sifting through the Roman remains which exist on this site. It really is a forest of piles, and it becomes apparent how easy you can fill up the ground with concrete if you're just putting more and more foundations into the ground. So if you want to avoid that and try to achieve net zero carbon foundations or carbon net zero foundations, we need to try and minimize the concrete we're using. And this is because the majority of concrete is made with cement. And cement, the global cement industry currently creates around 8% of global CO2 emissions. So if the cement industry was a country, it would be about a third in order of magnitude of global emissions. That's really quite significant. So minimizing concrete is absolutely crucial. We also want to minimize plant and supply movements, and that's linked to the amount of concrete we use, because quite a lot of the plant and supply movements are to do with moving concrete around, although some of the plant is to do with excavating holes on a site. And then using the piles for heating and cooling the building will allow us to offset our carbon emissions. And if we can do that efficiently, we should be able to move to carbon net zero foundations. So let's just think about the ultimate aim. If we can reuse our foundations, then we don't have to build these new foundations, and we don't have to worry so much about the concrete you're using, etc., etc. And that was something that we've really thought about a lot at City. So the innovative foundation that we've supported Keltbury Piling to develop is called the Hyperpile, and this is what I'm going to talk about today. The Hyper stands for Hollow, Impression, Precast, Energy and Reusable. I'm going to focus on why the pile is hollow, what the impressions add, the energy element and why the pile is reusable, but I'm not going to cover the precast aspect. This is a particularly bit of clever manufacturing that Keltbray have put together, and not my focus for today. So let's start with the problem of reusing the foundations. This has been an aim of the industry since the middle 2000s, mid 2000s, I suppose. And around that time at City, we had this idea that the way through this problem was to make the pile hollow, and we applied for a patent for this innovation, which was awarded in 2012, and we demonstrated that you could manufacture a hollow pile in 2008. And on the right-hand side, I've illustrated why making the pile hollow really helps reuse. So the first thing is that you've got your pile, it usually sits under a basement slab, and then it will support some column or something on top of it. And you need to know what that pile is. And one of the ways you can find out easily if you've got a hollow pile is that you can drill through the basement slab into the pile, put down a little camera or something like that, and look at the pile that you actually have. So you don't have to imagine what's in the ground. You don't need to be able to access records of what's in the ground. You actually know what's in the ground, and that is vital if you're going to try and reuse the pile, because you can correctly assess the pile's load capacity. The second advantage of a hollow pile is that it's relatively straightforward to extend it, and this will give you more capacity for your pile if you need it. And that would minimize the additional concrete that you need to put in the ground. So you're not creating a brand new pile, you're just extending an existing pile. So this was one of the drivers behind the City innovation of having a hollow pile. And there was another one, which is that it enables you to use the concrete in the pile much more efficiently. So this is our standard pile, and we've already established that this kind of pile uses shaft friction at the perimeter of the pile to support the load imposed by the building above. So it's primarily how these piles work. So the concrete in the middle of the pile is not really doing anything. Only a fraction of the concrete present is actually required to transfer the load from the building into that shaft of the pile. And you can keep the thickness of that pile annulus to around about 200 millimeters. You can support any axial loads you're likely to be able to apply if you keep it at this thickness. This has a dramatic effect on the amount of concrete you need, and hence the CO2 emissions as the diameter increases. And you can see this in the green curve here in the graph on the right-hand side. So here we've got a graph of carbon emissions in tons against board pile diameter. So in order to increase the perimeter of the pile, we need to either make the pile longer or wider. If we make it wider, then you can see that if it's a solid pile, that's the green line, the carbon emissions go up dramatically. If it's a hollow pile with this annulus of 200 millimeters, then you can see by the blue line that the carbon emissions go up in a more modest increase. So increasing the pile diameter as it happens is a particularly advantageous way of increasing your pile capacity if you've got a hollow pile, because particularly if you're constructing piles in London clay, what it can mean is you don't have to move the pile into the ground beneath the London clay, and that means it's much more straightforward to construct. It also means that you can use one pile rather than a number of piles in a group. So if you've got a large load and a single pile won't work, quite often people would put in a group of piles instead. The problem with a group of piles is that when they're closely spaced, their load carrying capacity reduces due to interactions between the piles. So it's not efficient. So the most efficient way in terms of concrete use is just making your pile a bit wider. So using concrete more efficiently by making the pile hollow is obviously a big step forward. But Keltbray wanted to do more than that, and they've developed a tool that can profile the shaft of the pile. So the shaft is where we're getting our load-bearing capacity. And the pile shaft is profiled before the concrete is added. And essentially, this is an impression tool, and I'm going to describe that in just a moment. And that creates impressions or nodules down the shaft of the finished concrete pile, and that increases the pile capacity without having to increase the pile diameter. So it's a more efficient way of giving yourself more pile capacity or a larger diameter pile, effectively a larger diameter pile. So this is essentially how it works. There's an impression machine at the top here lying on its side. This is lowered into the pile and it operates essentially in two halves. So there's this upper half where there are two shields. These are these sort of rusty coloured things on either side. And they're jacked apart by hydraulics which are in this middle section. And you can see that they have these bits of metal that stick out on each of the shields, and these create the impressions. And then on the lower half, once again, you have these bits of metal that jut out, creating your impressions, and then you have a shield. And it goes in the other direction, which means that at the top of the tool, you're pushing in one direction, one axis, and at the bottom of the tool, you're pushing in a different axis. And below is a typical impression, which is made by the nodules attached to the shields. And this has been created in a pile bore in London clay. And essentially, it's a picture which has been obtained by putting a camera down the pile bore to check out how the impressions have worked. And so this is an actual impression. And you can see that you've got a hole in the ground in the bore of the pile. And when you fill the pile with concrete, then the concrete is going to go into that hole and create your impression. The diagram to the right shows you how this typically works for a pile. So you lower your impression tool down the pile, you jack it apart to create the impressions, then you retract it so that these little bits of metal that stick out that create the impressions fit inside the bore. Then you raise it up the bore and then you jack it apart again to create another set of impressions. So the massive advantage of this approach is it's a very quick method and it doesn't hold up your construction very much, and it seems to work very effectively. So we at City have been working with Keltbray Piling and some other industry collaborators to do some research and development work funded by the government through Innovate UK, primarily to investigate and optimise the increase in load capacity provided by an impression pile. We're using our geotechnical centrifuge, which is an increasingly common piece of geotechnical testing apparatus that allows you to test small-scale models at increased G levels to ensure self-weight stresses are equivalent to the full-scale prototype. We generally test at 50 G. The apparatus can go up to 200. The centrifuge is an ideal method of investigating geotechnical structures where there is an interface between the soil and the structure, and that is the critical element. This is very difficult to model accurately using numerical methods. And in these tests, we were investigating how the soil deformed around the impressions at the perimeter of the pile. And so centrifuge testing was a suitable approach, providing good control of the geometry and the soil and allowing a number of tests to be completed relatively quickly. So for this project, which ran over 2 years, we ran 15 successful tests on more than 50 piles. So what were some key outcomes of these tests? So initially we were looking at the behaviour of the pile as it failed. So what happens is described in the graph on the right. You gradually press the pile into the ground and you measure the load on the pile as it settles, and find that at a certain settlement, the load is constant, however far you push in the pile. And that's when the pile has failed and indicates the pile's ultimate load carrying capacity. Typical results for the impression piles, that's the line in red, compared to the straight-sided piles, which is the line in black, show that if the position of the impressions was optimized, there would be an increase in capacity of around 40%. We found that the reason that this works is because of a block failure where the soil becomes trapped between the little impressions. So if I go over here, these are the impressions sticking out of the pile, and this is the soil which is essentially trapped between those impressions. So you get this block failure along the length of the pile. And this means that instead of just having soil pile friction along the shaft, there is soil-soil friction along these bands of soil which link the impressions. Now, as it happens, soil friction gives you the full strength of the soil, whereas soil pile friction, for London clay particularly, generates about half the strength of the pile. So not only are you increasing the area of the perimeter, which is generating this friction, but you're also increasing it by having soil-soil friction, which gives you additional strength. And that's why you can have really quite a significant increase in capacity for these piles, even if the impressions themselves are quite small, and the ones we tested were not quite as wide as the ones shown here. These are a width which is closer to what they use now in practice. So the other thing we found was that this block mechanism only occurs when these impressions are close enough together. So we found out what the critical spacing was for these impressions in order to ensure that you generated this block mechanism, and hence maximized the increase in capacity whilst minimizing the number of impressions that you needed to create. So in the first series of tests, we were looking primarily at overall capacity of the pile at large settlements, but during testing, we gradually increased the sophistication of the model pile we were using, culminating in the pile on the right, which was made in a number of different components, which all slotted together to create a much more realistic representation of the model pile and the contact between the pile and the soil. This enabled us to compare plain and impression piles from very small settlements all the way to failure. And the graph which is plotted here is a little bit more complicated. And this is essentially showing the load ratio. So the ratio between the load that could be taken by the impression pile and the load that was taken by the plain pile as you loaded the pile from very small settlements over here to much larger settlements over here. And again, we normalized the settlements by dividing by the pile diameter, but that doesn't really matter. You're just going from small settlements to larger settlements on a logarithmic scale. And that emphasizes the behavior at these small settlements. And it's the behavior at the small settlements that you're really interested in, because they represent the working behavior of the pile. So this green line is sort of the working loads, or the settlements at which you would be at working loads for your pile. And this line over here is where you would reach failure. So what you can see is there's an increase in load up to a factor of around about 2, perhaps a little bit higher over here, in the data from a series of tests we did on impression piles, and they're sort of summarized in this band of data here. And at working load, we're definitely around the sort of 1.8 to 2 times the load that you would get from a plain pile. So the other thing that we're looking at with the hyperpile is using the void for heating and cooling the building it's supporting. And below a certain distance, the ground temperature is quite stable. And so the water can be heated in the winter or cooled in the summer by passing it through a pile. To do this with the hollow pile, what you do is you fill the pile with water and then you put pipes into the pile. If it's cold, you'll pass cold water into the pile and you'll get warm water out through a heat exchanger, which is sitting at the top in your building. And that will enable you to heat the building. The combination of water and a narrow concrete annulus gives you a much more conductive thermal pile than you would have if you had a solid concrete pile, increasing the efficiency of the heating and in the summer cooling offered by the pile. It's also much easier to access these pipes and replace them if necessary. As I've said before, once you've opted for hollow piles, these can be of large diameter and not in groups, ensuring optimal efficiency in terms of both concrete and the heating and cooling process. So we're currently undertaking more model tests on our geotechnical centrifuge in order to investigate the thermal response of the ground when the pile is heated and cooled due to seasonal heating and cooling of the building. These tests are linked to some full-scale hollow piles with heating and cooling which have been constructed for HS2. The beauty of centrifuge testing for this application is that because the models are very small, temperature and pore water driven changes occur over small distances and are quicker, such that a change in temperature, which in a large scale prototype would take a year, can be modelled in a few hours on the centrifuge. So we can study many years of seasonal temperature changes in a way that just wouldn't be practical in the field, and we are currently collaborating with the University of Leeds and Imperial College London to improve analytical and computational methods used to predict how these thermal piles will behave. So I've told you a little bit about the development of our innovative foundation, the Hyper Hollow Impression Precast and Energy and Reusable Pile. And I hope that you can see that using this type of pile, which is hollow with impressions that reduces the concrete used, thus reducing emissions, that we can improve the productivity of using precast elements, and we can reduce operational carbon using geothermal energy storage, getting us towards carbon zero, and that we can reuse, thus reducing the concrete that we just leave in the ground, should create for us an energy generating asset, which we hope is the future of pile foundations. Thank you very much.
Thank you very much indeed, Sarah. Some very interesting stuff there going on underneath our feet. You said the city was awarded a patent in 2012, and as an emeritus professor of the university myself, I'm delighted to hear that. And you also mentioned building practice across Europe. Is this process being used elsewhere? Can you tell me?
So our partners in this piling are looking to use the process outside the UK, yes, definitely. And I can't talk in detail. We're at sort of relatively early stages, but yes, it's likely to be used on some very large projects overseas.
Yes. Well, I have a background of working with Mexico in particular, and of course earthquakes are a key issue there. I have to say in the dreadful earthquake of 1985, buildings dating back to the Aztecs didn't move. Spanish colonial churches didn't even lose their glass, and half the buildings constructed in the 1950s fell down. So obviously foundations are a critical topic. Now we've got lots of questions coming in. A good one from James Fleck. How does a forest of piles interact with all the tunnels and services which are underneath London?
So that's a problem actually. The ground underneath London is quite crowded. If you have piles in close proximity to tunnels, then they're not going to develop the capacity that you want, the shaft capacity that you want. And so you do end up in some circumstances extending them lower. Where you have projects like Crossrail, for instance, stuff like that, they will preserve the corridor well before the project takes place, so people can't put foundations which are going to interact with their projected train or tube lines, etc., etc. So it's a complex problem, and they obviously do have consequences on each other.
I assume you have some pretty good maps of subsoil London. Now,
Yeah.
one from a possible colleague, Chris Atkin, who I see is at the University of East Anglia. Very interesting talk, thank you. You did say you wouldn't speak about precast fabrication, but how does this work with the impression pile?
So essentially, they make precast sections and they drop them down the pile bore. So they open a pile bore, they drop the precast sections down, they tie them all together. It's a bit like post tensioning a bridge or something like that. And they leave a gap between the precast sections and the outside of the bore, which has previously been impressed. And then you can fill that with concrete that is designed in order to flow easily into cavities and things like that, and that will create a solid, structure with your precast in the middle, your void inside the precast section, and your impressions on the outside.
Right. Possibly a critical view by Hugh Purser, who thinks that the construction industry is a conservative one. How long do you think it would take to see widespread usage of hyper and thermal piles?
Yeah, I think that's a very interesting one. I think that it depends what the drivers are for the industry. And I think that the carbon zero driver, which is becoming ever more important because of the climate emergency, is one which is really going to force the industry into being a little bit more innovative. And I don't know that everybody will use the hyperpile, but I think that they will use versions of it because you need to it just offers you such a massive amount of benefit. Making the pile hollow is one of those things that's the gift that just keeps giving, to be perfectly honest. All sorts of
Well, it's a
benefits.
very original thought, I must admit. Now, Mark Cook says thank you, and here's one for the hydrologists. What's the differential between the cold and the subsequent warm water?
Well, it depends a little bit, but I think that we usually work on the basis of having about 20 to 30 degree, 30 to 40 degree difference, something like that. It's not my area of specialism. That's why we're working with Leeds. So we work with a wonderful academic called Fleur Loveridge there, whose area this really is. But yeah, I think that's about it.
All right. Now, with the Normalised lectures, we're very keen to hear about training and the future of particular industries. Rowan Anthony, Shirlington Barela, and Delprat Davids have asked about apprenticeships. Could we accelerate apprenticeships into hyper and thermal piles?
Well, I know that the construction industry are very keen on apprenticeships, and there are apprentices. I'm sure there are apprentices at Cadbury Piling and in many of the major construction industry groups, who are involved in these kind of projects. I talked a little bit about Innovate UK, and they fund not only sort of pure research like we did, but also something called knowledge transfer partnerships. And that enables us to get just graduates into a role where they can help us to do some R&D development. And we had such a partnership with Cadbury Piling, and we had a couple of graduates working in the project. And I think it's very exciting to be involved when you start in the industry in something which is a bit new and different, and where you're pushing the boundaries a bit.
Yes, well, I think partnerships between industry and universities is very, very important, and I hope some vice chancellors are listening. Now, James, again, given the sunk investment in previously installed old piles, is there not great merit in harnessing these for modern buildings?
Well, I think that's right, but the trouble is, it can be difficult to do so. So there have been some notable projects where people have reused foundations where they're just conventional foundations. Quite often that tends to be where, for whatever reason, maybe it's the same developer redeveloping, or the same person involved in the redevelopment as did the original one, but where there are records of what was actually constructed. And I think there is more reuse going on at the moment, but the current foundations are a little bit limiting in how you can reuse them.
You mentioned the Bloomberg building, which I found very interesting, not least because my daughter used to work for them. But that was an amazing piece of excavation. I'm afraid, with regard to the archaeology. What is the view of the engineers of the archaeologists, or the archaeologists' views of the engineers?
Well, I think that we all recognise, I think that under London, particularly, which is an ancient city, there's going to be valuable archaeological remains. And so one just has to accept that if you're going to do some work, then you're going to need to wait for the archaeologists to have a look at it. And that's a perfectly reasonable thing. And it was, I mean, I think when the original building was built there, so that it's the Temple of Minerva, I think, which
Mithras,
exists.
Mithras, yes.
Mithras, that's right, Temple of
Mithras,
Mithras,
oh, Mithras, yes.
which exists there. And um, so they moved it when they built the original building. They moved it, and then when they built the new building, they've gone back and found further remains. And I think there's a really interesting exhibition area on the edge of the Bloomberg building, which allows you to see, what they found and everything about the underneath and all the rest of it, which I think, is fantastic.
No, it's absolutely amazing. Well worth a visit because you actually go downstairs to the Roman level and almost to where the temple was located. And of course, there's some very modern audio-visual stuff there as well, which was really good. And of course, in the 50s, they just put it out in the open air on the surface, somewhere away from the original. At the Stationers Company, we had some recent experience of working with the archaeologists because not far from Paternoster Square, dig down 2 feet, you'll find something. And the building work was halted for a couple of months. And we got very excited because we came across some dark material, which we assumed was ash from the Great Fire. So we had this wonderful idea of having souvenirs and things like ashtrays with genuine ash from the Great Fire of London, till the archaeologist pointed out patiently that actually this was 19th century City of London poo. So we were unlikely to be able to market that. Anyway, coming on to large holes in the City of London, every time I come up to town, I find a building I once knew has been knocked down. I can't remember what it looked like, and there's a hole 200 feet deep. Now, digging a hole 200 feet deep, where does all the spoil go to? Is that the responsibility of the engineers, or is that a completely other, different part of industry?
It's the responsibility of the construction company to decide where they're going to dispose of the spoil that comes out of the excavation. And nowadays there are very strict rules about how you can where you can put that material. There are taxes on moving the material off site into somewhere else. And if you have a really large project, then they think very carefully about where they're going to put it, and they can create or have created in the past new sort of islands and wetlands and things like that in order to create natural environments out of the material that's taken out. In London, a lot of this material gets moved down the Thames. So it's just taken to barges to move down the Thames because then it's not cluttering up the streets.
Well, I sincerely hope they don't bring any of it to my garden because we're on London clay and it floods every time there's a storm. But never mind. Yes, the other thing that occurs to me is the right in the heart of the square mile. There's this very concentrated number of what are now very tall buildings. There was a time, I think, when buildings stayed at 8 and possibly not more than 12. If you put one enormous building next to another building, whether it's large or small, does that have an impact on the foundations of the other building? Do you have to take that into account?
Yes, I think you do, but it depends how close they are. So there are interaction factors that tell you how the load carrying capacity of the pile is going to vary depending on how close it is to another pile. Generally speaking, you'll find that those piles are not necessarily that close to the other piles, so they're not going to have a huge impact on each other because that interaction factor falls off quite rapidly as you move away from the pile.
Yes, with regard to very modern buildings next to historic buildings, I know of one Oxford College that has 17th century buildings which seem to have large oak um, trees holding the actual building up. In London, we do have, I mean, you think of the Wren churches, for example, which are magnificent. I don't know what kind of foundations they have, but again, is there a problem if you're putting modern foundations down next to what I might call historic ones?
Well, I think you'd assess that and you try and ensure that you went deep enough to ensure that you weren't affecting the foundations which were adjacent to you. So yeah, I mean, quite often you're going to cause more damage by excavating the bores for the piles than perhaps actually putting the piles in and then loading them with your building. So of course you have to be very careful about what you do, and there are lots of party wall agreements and things like that where people try and work out what's allowed and what isn't allowed.
I have harsh experience of party wall agreements myself in a two-storey building, so heaven knows what you have for a 12-storey one, never mind. Now, time is getting on, I'm afraid. It's a very interesting topic and some fascinating information there, which I certainly knew nothing about. But I do see that you're quite modest, because you're actually a past master of the Worshipful Company of Skinners, and you do a lot of work in the field of education. Can you tell us a bit more about that?
So the Skinners Company, education is one of its big things. It's no, well, it hasn't been for over 100 years in any way involved in the fur trade, which was its official, was a original sort of trade that it was set up. Well, sort of. It's a fraternity, so it's not quite like some other livery companies. But anyway, its main thrust at the moment is education and supporting young people and also elderly people. So we have, I think we have around about 7,500 students that we're supporting at the moment. So in schools, so pupils in schools, in our family of schools, and those schools are both independent, state, grammar, all ability, etc., etc. They're mostly in Kent and in North London. And I'm involved in the Skinners Academies Trust, which is a group of 5 of our academies, which has recently come together to really cooperate and look to, support our pupils to achieve as well as they can and to drive up standards. So that's very exciting for me. We also give grants to young people at City University. We're supporting nurses studying here, and we support lots of young people going on various vocational courses and things like that. And then we have 2 almshouses. One's an extra care one in North London, and so this is sheltered housing for elderly people. So one's extra care in North London, and the other one is in West London, and it's just a standard almshouse.
And you do all this in your spare time, of course.
Well,
This does
I'm
give
not
you
involved in all of that.
this does give you a great opportunity to plug the STEM subjects. Do you do that in particular by any chance?
Yeah, to a certain extent. And I think it also gives us an opportunity to provide pupils with a chance to get to grips with what university study might be like. So, I have invited students or pupils from our schools to come and spend a little bit of time at City just to get a sense for what happens here, because many of them are first time university entrants if they do decide to go to university. So yeah, that's nice. And for me personally, I'm passionate about education, and to understand the pupils and students who are coming from schools into education in a university is a vital thing, because what one wants to do is ensure a really good transition to university studies.
Yes. Are you finding more girls are coming into engineering?
Marginally. It's not like the law or something like that where there's been
Yeah.
a real sea change.
Yes, yes.
Oh,
Well, it's very interesting to hear about all the work being done with education and training by the livery companies. And later on in the Mayor's Year, which goes through to November, we will be looking at this in more detail with regard to the livery companies as a whole. But I'm afraid that's all the time we have for questions. Can we have a quick look at what's coming up? We have inclusive leadership through the lost my screen there, through the lens of behavioural science, embrace diversity and improve productivity, 2 very common subjects now, very important. 25th of January, the Beware the Techno Fixes draped in sickly green. I think you'll have to tune in to see what that's about. Tuesday the 30th of January, gosh, now here's a very current subject. What does quantum computing mean for cybersecurity? And you can find all of our lectures, which are recorded, posted on the Gresham Society website, on our YouTube channel, in case you want to revisit anything. And we hope to see you all again for another lecture in the Knowledge Mile series. And don't forget the Mayor's theme for the year, Connect to Prosper. So thank you very much indeed to Professor Sarah Stalibras, City University of London, another quick plug, and we look forward to seeing you all again at another one of our lectures. Thank you very much indeed, Sarah, and goodbye.